Right. The next topic is related to Fourier series. You know, a signal, a continuous signal in time domain is either aperiodic or periodic. We notice that a pulse in time domain is aperiodic. But right now, we want to concentrate on periodic signals, analog periodic signals, okay? We can find Fourier series for them. What's the equation? You see here. Ck is equal to what you see. Here we may use x tilde or just simply xt. It's not important. You shouldn't care about it, but you should know about the nature and the nature of the signal. Okay, it's periodic with some period, which is called T0, T naught. So we'll have omega naught or omega 0, and it's related to F0, which is the frequency the signal is repeated, or in time domain or frequency domain. Okay? So Fourier series and Ck coefficients are discrete in nature. We'll see in illustration very soon. But x of t is continuous. Here you see how it's reconstructed, a signal is reconstructed from Fourier series coefficients. So please write down these equations. And moreover, what's Fourier transform for periodic signals? We write down very important equation. It will be 2 times P times Ck. Try to remember it. 2 times P times Ck, but using Dirac signal, impulses, with a distance omega 0. Okay? The nature of x of capital omega will be continuous, while the nature of ck's are discrete. Please write it down. Okay. Here you see ck for a cosine. What's the signal? Find Fourier series of x1 of t cosine omega 0t. And the second signal having a nature of sine. Okay. We consider the first one. x1 of t is equal to cosine. We find that there are only two coefficients, c plus 1 and c minus 1, both equal to half. Here illustration completely shows, okay? Its amplitude and the phase is everywhere 0, not. Okay? Again, c minus 1 is just 1 over 2, half. And here you will remember it. It's very important information. And the nature is discrete. Here you see it. It's not continuous. Okay? Amplitude and phase of the Fourier series of cosine. Now, another question. Investigate that for a real periodic signal, the amplitude of Fourier series is always even and its phase will be odd. Again, amplitude or apse is even, the phase will be odd. If the signal in time domain is real, but if it's a complex signal, you will not have the same idea. Right. Another part of the question. Find and plot the Fourier series of cosine having a phase plus phi. So you'll reach to the just this answer that the amplitude again will be the same, but here you'll have a signal appearing here, e to the power of j phi, and another one will be complex conjugate over c minus 1 e to the power of minus j phi. But please reach to such answer. Right. Now, the second signal, sine. Very simply, you'll find that the amplitude is again 1 over 2 or half. Here, 1 over 2. But the phase for the first one is minus pi over 2. And for the next one is pi over 2 or 90 degree. C1 will have a phase of minus 90 degree because J is here. Okay? Another question. Provide similar take-home for a sinusoidal signal as done for the first one, cosine. And the second part, find and sketch the Fourier series of impulse train. Impulse train is again a periodic signal and very important signal. Discuss about its amplitude and phase similarly in a similar manner. And claim that again amplitude will be even and phase will be odd. Please write it down and keep it for future usage. Right. Another problem, sifting property. It's called sifting property. What does it mean? If we have a multiplication of a signal with a Dirac, okay, x of t times delta of t, the result will be x of 0 or not times delta of t. Okay, just imagine its plot. How will it appear? The next one, x of t times delta of t minus tau, a shifted Dirac. So the result will be x of tau times delta of t. And another imagination, if we have a impulse train, delta of t, delta of t minus 1, t minus 2, blah, blah, and from left side, t of t plus tau plus 2 times tau, blah, blah, meaning that you are considering impulse train. So what will be the result? Okay, it's picking the amplitude of the input signal called x of t with specific distances. In other words, it's sampling. Okay, we'll later concentrate on the problem. Right. The next topic is related to convolution. Convolution is again another important topic. To start with it, we say convolution of two continuous time signals. Later, we'll have a discussion related to discrete time signals, of course. For instance, let x of t and h of t be the input signal and impulse response of an LTI. You should remember from Signal and Systems course what LTI is. Of course, we'll explain it in brief. Linear time invariant. The exact idea is in analog we have time, but in discrete purpose we have shift. There is no time. Later we'll be familiar with it. But for now, LTI, linear time invariant system. So again, x of t is the input to the system, and h of t is the impulse response of the system, assuming that the system is a linear time invariant. Okay. What's the result? What's the output called or denoted y of t? Please write down this equation. It's very important. Y of t is equal to x of t ast. It's called ast, a symbol for convolution. It's conventional. You may use any other symbol you wish. But the equation is very important. Integration, you see from minus infinity up to plus infinity, x of tau times h of t minus tau dt. Or similarly, we say the first signal, the second signal. It doesn't, it's not important. You may change their position. Say the first one is h, the second one is x. So the result should be the same. X of tau, h t of tau, t minus tau, or h of tau, x t minus tau. The same result will happen. Okay? So, you wrote it down for further usage. Now, the question. Prove that if y of t is equal to x of t as h of t in time domain, meaning that convolution in time domain will lead to the multiplication of their spectra or frequency response, or just h of omega is called system frequency response, and this one is Fourier transform of the input signal, capital X of capital omega, meaning that the convolution of two signals in time domain will lead to the multiplication of their Fourier transforms in frequency domain. We mentioned what h of omega is called. The second one, also investigate that the multiplication of two signals in time domain will lead to the convolution of their Fourier transforms. Okay? It's called dual property. Multiplication in time will lead to convolution in frequency domain and vice versa. Convolution in time domain will lead to multiplication in frequency domain. What does it mean? Here you see x of t, if it's multiplied by p of t, okay, multiplication in time, it will lead to convolution in frequency domain. Of course, if p of t is a cosine signal or impulse train, it will have a spatial meaning. If it's a cosine with frequency higher than the max frequency in input signal, you have learned it in BSc courses. It's amplitude modulation. Okay, but if it's an impulse string, okay, it will be sampling. So two applications from this very simple equation. Now, prove that x of omega convolved with delta of omega will lead to x of omega. Okay, please consider this equation. The next one, x of omega convolved with a shifted Dirac, it will lead to shifting the same of input signals spectrum. Okay? Again, please write down these equations and compare such property with sifting property already mentioned. And another question, discuss similar idea in time domain. Okay? So you'll have x of t convolved with delta of t will lead to x of t, and similar idea for the next one.